The last speaker for our session is Hendrik van Broekhuizen, and he will be presenting on purrr beyond map.
Okay, thanks so much for this opportunity. I want to start off with an embarrassing confession. I've made a rookie error. First, I've got too many slides, and then I've also included an abundance of code on those slides. But fortunately for me, and I think for you as well, I do believe these slides are going to be available to all participants after this. So I'm going to jump over some things quite quickly. My name is Hendrik. I work at a data science product development company in Stellenbosch. And it's my privilege to talk to you about purrr. So you've all been sitting, listening intently. I quickly want to get a bit of audience participation. So hands up, who's never heard of the purrr package? It's quite a few. Hands up, who has heard of the purrr package? Hands up who didn't understand the question and didn't put up their hands either the first or the second time. Okay, so let's dive into what is purrr. So purrr is a consistent and complete functional package, functional programming package for R. And R is not a pure functional programming language, but the intention of purrr, at least initially, and I still believe it is to give you the same kind of expressiveness in R code that you might find in a functional programming language. Of course, the star of purrr is map. It's the poster child, really. So who's heard of map? Okay. I could swear there were more hands that went up now than who's heard of purrr, but okay. Who's heard of lapply, or the apply family of functions in base R? For loops, right? So we're talking about iterative operations. So map is the poster child, but it's a little bit like looking at a wardrobe and saying, that's a really nice wardrobe, but never going through it and actually seeing Narnia. Because the other functions is where I believe purrr really gets very, very good. Unfortunately, they don't get as much press for a variety of reasons. But I think that purrr has one of the highest rates of return on investment. So it does require investment, but like any good mystery, it reveals itself slowly, and it just keeps getting better and better and better, unlike Game of Thrones at the end. So what is it good for? Quite a lot of stuff. So the first thing is iterative tasks. I see it as a supercharged lapply family, lapply++, if you like. It's also really good for working with lists, particularly complex nested lists. I don't know of anything else in R that's quite as good for doing that. And then there's a thing that people very seldom mention, or I see mentioned very seldomly, to create really robust, flexible, and consistent routines and functions. Things that fail loudly when they have to, or fail completely silently if you choose to force them to do so, and have consistent syntax. So let me give you a quick primer on map, just so we all work from the same benchmark. I'm going to go quite quickly here. So map says, take some kind of vector and pass it into this function. You have a function and you want to apply it to each element of that vector and then spit out a list. Okay? Similar to what you might do for a for loop, right? Apply this function to each element that I'm passing to you. Okay, so this is basically the syntax, what it looks like. I've defined a function there that's already vectorized that doesn't need to use map, but that's how you would use it with map, and out comes a list. If you add a suffix after an underscore to this, you can actually coerce the list that it produces into an atomic vector. If that's a character vector, numeric vector, whatever it might be. So here I've got exactly the same code that I showed in the previous line, but each time the resultant list is just being coerced to a type. Okay? Of course, if you can't coerce those elements to that type, it's going to error out, right? You can't expect it to produce a data table or a data frame if you've passed it a vector of characters. So this is where the talk actually starts. Map variants. I'm also going to talk a little bit about predicate functionals and adverbs. So map has siblings, walk and modify. They do exactly what map does, except where map returns a list, walk returns nothing, or returns its result invisibly. Modify returns exactly the same type as the input. So what does that actually mean? So let's focus on the left-hand side first. I've got the numbers 1 to 5 being piped into a walk function. So what I would expect if I pipe this into a map function is it's going to produce a list with 1 min, 2 min, 3 min, 4 min, 5 min. But there's nothing there. Okay? Weird, if you've never encountered walk before. So maybe I missed a print function at the end. So in the second block, I pipe that into a print statement. Now I get output, but it's not the output I expect. It's the input vector. What's happening is walk actually does the stuff I'm asking of it to do, but then it chucks it away as soon as I exit that environment. And then it returns the input vector again. I'll get to why that's useful in a second. Modify, on the other hand, I don't have to go into too much depth. What I'm trying to do here is I'm trying to coerce a character vector to integer. Modify is not going to allow you to do that. You've put in a character vector, you have to get out a character vector. Why is this cool? If you put in a data table, you're going to get out a data table. Okay, so why would you want to use this? Walk is just do stuff. You don't always have to actually return output that you want to store in an object. So you can think of the message command or the cat command or disk operations in particular, right? They don't need to return anything to you. It also allows for pass-through. Pass-through is less important, so you can conceivably think of piping something into a walk statement, doing stuff, and then continuing on with the input as though you hadn't actually interrupted that operation at all. With modify, the argument is that sometimes type preservation is essential for your routine to actually work. You don't want to accidentally change the type. And I'm going to show you an example of that in a second. So there are more variants to map, and I'm not going to go through all of them. But what is the takeaway point from this? All the map variants are orthogonal in terms of their inputs and their outputs, which means you can put them in this neat little matrix that tells you which one you should use for which use. But the basic rules are this. If you want to list, use map. If you want to coerce that list to some kind of atomic vector, use a suffix. If you want to return the same type as the input, use modify. If you don't want to return anything, use walk. If you have more than one input, 2, add the 2 as a suffix. If you want to iterate over a vector and its index, use I as a prefix. And if you have many, many arguments, many, many inputs, use either pmap or pwalk. So let me give you an example of using walk, what I think is quite a cool example. I'm going to use the MPG or MPEG data frame from ggplot. Hopefully most of you are familiar with it. What I want to do is I want to say for each manufacturer in that data set, I want to write to disk a CSV that contains only its data. So how can we use walk for this? First, I just want to illustrate that I don't actually have any files on disk. So proof, there's nothing there. A lot of code, you can get all the gray, that's just me commenting out. I'm going to basically read what the code says. So take the MPEG data frame, pipe it into a group nest statement from dplyr. What that's going to do, it's going to collapse the data. You're going to have 2 columns. One called manufacturer with 1 row for each unique level of that manufacturer variable. And then another column called data that contains the data only for that manufacturer. That's useful because now I can pipe it into pwalk. And I can define a function that iterates over those 2 columns, row by row. Within this statement, I'm just defining a file path. Okay, so I know some of you may not be familiar with the glue, but it's like paste. So I'm literally just pasting pieces together to get a valid file path, and then I'm writing this out to CSV. And it works. So here I'm listing the files again, just showing the first 2 and the last 2, but now they're there. I've got another example here that uses iWalk to do the other way around, to from disk read things into memory, into the global environment. But I'm going to skip over that and show you modify. So for modify, I want to express each of the numeric columns in the MPEG dataset as the percentage deviation from its mean, but I want to do this by the manufacturer. Okay, so within each manufacturer group. So I'm defining a little function that will do that. If I pass it a vector, it's going to express it as the deviation from the mean. And I've got 2 code chunks here. The one on the right, for those of you who are, what do you call someone who likes the tidyverse? Good people. For those of you who are good people, on the right-hand side, tidyverse, this should look fairly familiar to you. On the left-hand side, I've used data table and modify if to do exactly the same thing. And I can prove that the results are equivalent. Okay? So with modify if, in some senses, you can bring a little bit of dplyr-esque coding into data table if that's your fancy. Predicate functionals are the opposite of Schrödinger's cat. They return a single true or false value and do something useful. So I'm going to show you 2, every and some. I want to know in the MPEG dataset which manufacturers have models where all of those models exceed 15 miles per gallon in cities, or at least some models exceed 25 miles per gallon. So the important bit here is what's happening there. All I'm saying is I'm passing that vector to the sum and the every statement, and it's going to spit out answers for me, and it's going to tell me whether all of the values in that vector satisfy the condition, or at least some of them do. Other vector transformations. This is the good stuff. Reduce and accumulate. So these use a function to combine the elements of x into a single value by taking the results from each iteration and passing it as an initial value to the subsequent iteration. Accumulate is exactly the same as reduce up to this point. Reduce returns the single final value. Accumulate returns every single value from each iteration. What does that mean? So I've created a summation function here. The two expressions in the first code block are effectively equivalent. I'm piping the numbers 1 to 5 into that reduce statement. The first time it sees the value 1, it's the initial value. It doesn't have anything to do with that. It's going to pass that back into the second iteration. What is the initial value to start off with? What is the value that was produced by the previous iteration, i.e. 1? What do I want to do with that? I want to add the next number to it that produces 3. Next iteration, and so on and so forth, right? And ultimately, I get the cumulative sum of those values. On the right-hand side, I just see every step along the way. So why is this useful? For reduce, it's when you basically want one thing, but getting that one thing requires repeating effectively the same additive operation over and over again. With accumulate, it's slightly different, as you're interested in every step along the way. You want to build something up. Maybe you want to build up a complex mathematical sequence or a graph, or as I'm going to show you now, a model. So I'm going to start off with the base model. I'm going to go through this quite quickly, where I want to just define a linear model, and I want to express city as a function of the manufacturer. And then incrementally, I want to add terms to this model, estimate all of them, and then get the R squared. Okay, so the key thing here is I'm defining models as an object. I'm piping a bunch of terms into the accumulate statement. I'm giving it an initial value. And you can see from the output that's produced down here what happens every single time. It just adds it to the model. Why is this useful? Because now I can pipe that into a map statement that fits each of these linear models. Then I can get a summary of that list of fitted models. From that summary, I can extract the adjusted R squared, and then I can print all of that nicely in a frame. Last one. I'm going to run a little bit over time. Adverbs. Adverbs modify the action of a function. They take a function as an input, and they produce a function as an output. So these are quite dear to my heart. Sometimes functions fail. If you've ever called an API from within R, I'm sure you know that very well. If you've ever scraped data from a website where the structure has changed and you weren't aware of it, you'll know this. Okay? So good coding involves putting in safeguards that tries to account for that. But sometimes things still fail. And you don't always want your routine to just bomb out because one thing has failed. So these functions allow you to deal with errors. Safely passes back a list of two values, result and error. Result will have something in it if there was no error, and a null for the error, or the other way around. Possibly says, if there is an error, continue onwards, but give me a default value rather than just the error. And then insistently says, try and try again for however many times I tell you to. So I've got a little example here, and this is the last one I'm going to show you. I've defined bad func here. Bad func doesn't do anything useful. It returns its input, but only if that input is an odd number. If it's an even number, it's going to give an error. So to create safe, possible, and insistent versions of this function, I just wrap them in those statements. And now I can show you what the results of those functions are. So left-hand side, good value. Right-hand side, bad value. Bad func is just going to error out with a bad value. Okay. Safely bad func is always going to return a list with two elements, result and error. And you can see that they just swapped around, right? Possibly gives me the correct value when it's a good value. It gives me the default value I assigned the bad one. Insistently says it tried 4 times and then it errored out. So why would you want to use this? Safely, you want to use if you want full control over how you deal with errors. Maybe the nature of the error is important for what you're going to be doing next. You want to continue, but you want to deal with that however you see fit. Possibly, you care that an error happened, but not enough to really care about the reason for it, or you know very well what the reason is, so why do you need it to tell you? You just wanted to continue on and not bomb out. Insistently really only makes sense if you expect the result from a function call to change over time with repeated attempts, right? So with this particular example, that's a silly thing to do. It's always going to fail. There's more purrr functions, a lot more, and they're all awesome. So you're intrigued? Of course you are. Where can you go to find out more about this? From within RStudio, it's fairly easy. Use the standard things that you would use to get help for any function. There's the purrr reference guide. There's an awesome cheat sheet. And then there's some really, really good tutorials online that I've listed here. And I would encourage all of you to go and have a look. Thanks.